I'm going to work through this 5.1 quick check. So start off, we're talking about propanoic acid, which is a 3-carbon acid that has a COOH. Anyway, it's a weak acid. Here's the Ka given right here, and we're going to need that. So first, write the net ionic equation for the reaction between propanoic acid and potassium hydroxide. So we're talking about H3H5O2. We're going to mix that with potassium hydroxide, and the OH and the H are going to turn into water, and we're going to get potassium propanoate out of this. Okay, and this is a strong base. It's going to completely break up. This is a weak acid. It's going to stay together. So our ionic equation will simply be the acid plus the OH, the potassium, will be a spectator ion. That's going to turn into, it's going to turn into water. And we're going to have potassium, that's a spectator. We're just going to have this ion, negative ion, left over. Now I put a single arrow because these neutralization reactions are very product favored. Okay, the formation of water really drives this reaction forward, and if we wanted to go back and calculate the value for this reaction, it's going to be somewhere in the order of 10 to the 10. So it's just, it's pretty much a single arrow. Find the number of moles of the propanoic acid in 20 milliliters of 0.2 molar. Okay, the thing I always remember is that volume times molarity. Okay, that gives me the number of moles. So my volume is 20 milliliters. And I'm going to change that to liters. And multiply that by the molarity, 0.200 moles per liter. So liters drop out, milliliters drop out. So 20 times 0.2 divided by 1,000. I get 0.004. And it looks like 3 significant figures, so 0.00400 moles of the acid are in here. Okay, now find the pH when 5 milliliters of the 0.4 molar KOH is added to the solution in question 2. Now the idea here is that because we've just added the acid and the base, okay, and this is a very product favored reaction, then we're going to do an icebox just to figure out what's left in the solution after everything has reacted, all the acid and base have reacted with each other. So first thing I want to do is figure out how many moles of my base do I have, and so I have 5 milliliters, and I'm going to change that to liters, and multiply that by its molarity, so 0.400 moles per liter. And so again, just like I did before, that the volume times molarity gives me the number of moles, and this time I'm going to have 0.00200 moles, and this is my base, whereas before this was my acid. So I'm going to set up an icebox, and this is going to be a stoichiometry icebox, and I'm just going to put it right here because of the fact I'm using this equation that I have up here in question 1. So everything is lined up. And I don't need the, I do need that. I'm not going to use this one, the water. Okay, so the idea here is my acid is 0.00400 moles. And my base is 0.00200 moles, and I'm starting off with no acetate. And so you can see what's going to happen is that I'm going to use up all of my base because I haven't got enough base. So minus 0.00200 minus 0.00200. And since this is a 1-to-1-to-1 reaction, this is going to be positive 0.00200 moles. So at equilibrium, this is going to be 0. I'm going to have 0.00200 moles and 0.00200 moles. Okay, so now I'm going to actually go back and do another icebox where I want to figure out, well, what is the pH of my solution? Okay, I want to answer my final question. And what is the equilibrium I have? This is just, I really have an acid-base equilibrium. I really have an acid equilibrium, I should say. Okay, I did a reaction which is changing my chemicals, but the actual reaction is the one here with the Ka. Okay, so HC3H5O2. So I'm going to write that again. Okay, and that is dissociating a little bit into H plus and C3H5O2 minus. Okay, that's the actual equilibrium I'm interested in. And for that, I'm going to do an icebox. Now again, I left out the water. I could have put water in H3O plus, but I didn't. And I have values here. Now what do I have? I have this many moles and this many moles. Okay, but what's my total volume? My total volume is I had, where did it go? 20 milliliters of my acid. I had 5 milliliters of my base. So the molarity is going to be these moles divided by 0.025 liters, 25 milliliters. 0.025 liters. So I'm going to get the same answer in both cases. And I calculate that as 0.08 molar. Okay, and that's there. And also here, 0.0800 molar. So I figured out my moles and figured out my moles, and I think that's easier to do with moles, and then divided by my total volume, so I have my concentrations. Now I could have gone and done everything in concentrations ahead of time, but I just think this is easier. Okay, so now we're just going to do a standard icebox. Okay, obviously this reaction is going to have to shift to the right because this is 0, no way it can shift to the left. So this is minus x plus x plus x. 0.0800 minus x and 0.0800 plus x, and we're going to put this into our Ka expression. So the Ka expression is H plus concentration times the concentration of C3H5O2 minus all over the concentration of HC3H5O2. And we have a value for that, 1.3 times 10 to the negative 5 that we have in the beginning of the problem. And now standard thing. Okay, we're going to say assume that x is much smaller than 0.08. Okay, therefore 0.0800 plus x is approximately 0.0800, and 0.0800 minus x is approximately 0.0800. So there's more there. I didn't leave myself room to fit that in. Okay, so let's substitute in. I have x times 0.0800 divided by 0.0800 equals 1.3 times 10 to the negative 5. So we can see that our value of x is 1.3 times 10 to the minus 5. Okay, molar, what is that? That is actually my H plus concentration. So that means my pH turns out to equal 1.3 times 10 to the minus 5. I said that wrong. pH is the negative log of 1.3 times 10 to the negative 5, which is going to be 4 point something. And in fact, that is, I get 3.586, okay, which I would probably report as 3.59. Okay, so that is the pH I would get from putting 5 milliliters of my base into the 10 milliliters, no, was it 20 milliliters of my acid. Okay, and we can kind of see what's happened here is I have twice as much acid as I have base, so I've neutralized half of my acid. So this is actually halfway to the equivalence point, and the pH equals the pKa. Okay, in other words, because these cross out here, the H plus equals the Ka, so the pH equals the pKa 3.59. And if I'd realized that earlier, I probably could have skipped some of this work. Okay, next thing. Find the pH when 10 milliliters is added. Okay, well, this is a different situation now. 10 milliliters of 0.4 molar. Okay, now we knew 5 milliliters was 0.0200, so now we just know that this is 0.0400 moles. Okay, and I think I left off a 0, so 0.004000 moles of OH minus. And we knew from before doing this that this is 0.00400 moles of H plus. So that means if I mix these two together, if I go back to my original equation, that if I have my acid and I mix in the same amount of base, then all of this is going to be gone. All I'm going to have is a solution that contains water and the conjugate base of this weak acid, so C3H5O2 minus. And that's the key ingredient here. So how much am I going to make? Well, if this was 0.00400 moles, and this was 0.00400 moles, okay, I was trying to skip this icebox, but I think I need it. Then you can see what's going to happen. Both of these are going to get totally used up, and I'm going to make 0.00400 moles of my propanoate. So what do I have? 0.0400 moles. And what if I mix together? I've mixed together 20 milliliters of my acid, 10 milliliters of my base. So my concentration will be this many moles divided by 0.030 liters, 30 milliliters. So the concentration of this ion, which is what I care about, will be 1.333 repeating. Okay, so that's constant. Now that's a useful thing. Now, how am I going to get a pH of this? Well, this is a different situation than we had before. This is not an acid dissociation situation. Now I have all the thing I have in my equation is the conjugate base of my weak acid. So my equation, my equilibrium is going to be C3H5O2 minus, and when it mixes with water, then I get C3H5O2 and OH minus. So this is the kind of a standard icebox, okay, for a solution that has the conjugate base of a weak acid. Okay, and I know that this original number here is 1.33 molar. And I'm just going to do an equilibrium, so minus x plus x plus x. So this will be x, and 1.33 minus x. Okay, so far so good. We need a k for this. Okay, so I'm going to go back and do a k really quick. And the k, this is the kb, and this is the kb that I'm going to calculate by using the Ka of the propanoic acid. So it's going to be 1 times 10 to the negative 14 divided by 1.3 times 10 to the negative 5, and that comes out to be 7.69 or 7.7 times 10 to the negative 10. Now that is a very small number, so that means I can make my assumption. So assume that x is much smaller than 1.33, and that's pretty easy. Okay, so therefore 1.33 minus x will be essentially the same as 1.33. Okay, so now I'm going to go back and do my Kb expression, and the Kb expression will be acetic acid, and not acetic acid, propanoic acid times OH minus all over the propanoate ion, and that's going to equal 7.7 times 10 to the minus 10. Now again, we're back here on familiar territory. Okay, we've seen this kind of stuff before, so this is x squared over 1.33 is equal to 7.7, this is molarity, 7.7 times 10 to the minus 10. So x squared is equal to 7.7 times 10 to the minus 10 times 1.33. And what I really want is x, not x squared, so I want the square root. And just to remind ourselves that x this time is the OH minus concentration. So there's going to be a POH involved. So x is equal to, I get 3.198, so I'm going to say 3.2 times 10 to the negative 5. That's my value of x. So therefore my POH is equal to the negative log of 3.2 times 10 to the negative 5, which is 4.495, so I'm going to say 4.5. And my pH is equal to 14 minus my POH, which I can see will be 9.5. And that's my answer for this. Okay, so the pH, when I've added 10 milliliters, this is actually at my equivalence point, so I have a solution that is the conjugate base of my weak acid, and that has to be treated slightly differently. So I still did my stoichiometry icebox. I figured out my concentration of what's in the solution, and then I had to do a hydrolysis equation showing here the conjugate base of the weak acid, and after that it's pretty straightforward stuff, and we were able to figure out that the pH is 9.5. Now, next part, find the pH when you have 15 milliliters. Now this is, again, is a slightly different problem, okay, because what happens, we still have, 0.0020 moles, no, I'm sorry, that's wrong, 0.0400 moles of our acid. Now if I have 15 milliliters of my 0.4 molar base, then we can just tell what we have. We have 0.006 moles of OH minus. Now this is a slightly different situation, because now once we've gotten past the equivalence point, then what we really have is a solution of excess hydroxide, and the hydroxide is so much more stronger than the conjugate base of this. We don't have to worry about equilibriums and conjugate bases. Okay, so let's just do our icebox here, figure things out. So here I have my acid. We're going to put in some base. We're going to make water, and we're going to make conjugate base. So this is our stoichiometry icebox. And the acid is 0.00400 moles. The base is 0.00600 moles. And we're going to use up all of our acids, so minus 0.00400 moles, minus 0.00400 moles, and we're going to have plus 0.00400 moles. Okay, now this will be 0.00400 moles, this will be 0.00200 moles, and this will be 0. Now it turns out that for this reaction, this is really so much stronger than this, that the pH is going to be based on the OH minus concentration. So I'm going to say, well, how much would I have? 20 milliliters, I have 15 milliliters, so 35 milliliters. So my concentration of hydroxide is going to be, 0.035 liters. So the my hydroxide concentration is 0.00200 moles of hydroxide divided by 0.035 liters, and I get 5.7 times 10 to the negative 2 molar. Now if that's my OH minus concentration, then my POH is the negative log of that number. Which I get 1.24. Okay, and my pH is 14 minus my POH, and that comes out to be 12.7569, so it's 12.76. Okay, those add up to 14. So here's my pH at that point. Now, I'm going to take all that information, and we want to kind of do our pH curve. Okay, for this we still need one value. Okay, so we have a number for when we have 5 milliliters, we have 10 milliliters, we have 15 milliliters. We really need to do one more and say, well, what would be our pH at 0 milliliters? Okay, because our original problem here was that we had a 0.2 molar solution of this propanoic acid. So let's go down here, and if I had propanoic acid, and that just broke up to be H plus and propanoate. Okay, and if I knew that this was 0.2 molar, let me double check that. Yeah, 0.2 molar. Then the question is, what would be the pH at that point, 0.200 minus X? Now we know that the Ka for this is 10 to the minus 5, so we can assume that, that X is much smaller than 0.200, therefore 0.200 minus X is approximately the same as 0.200, and now substituting that back into our Ka expression, which equals 1.3 times 10 to the negative 5, which was given to us at the start of the problem. So I can substitute these values in, and so I can have x squared over 0.200 is equal to 1.3 times 10 to the negative 5. So therefore x squared equals 1.3 times 10 to the negative 5 times 0.2. And I don't want x squared, I want x. So that's the square root of x squared, that's the square root of that expression. And x in this case is our H plus concentration. So we can find that the value for this is 2.6 times 10 to the negative 6. And that's the value, so I want the square root of that. So that'll be 1.6 times 10 to the negative 3. And I want that's going to be my H plus concentration. So the pH equals a negative log of 1.6 times 10 to the negative 3. And we can see that's going to be a value somewhere around 2. And if I take the log of that, it's 2.79. So 2.8. Okay, so what are my values? I have 2.8 for my initial value. So at 0, it's 2.8. That's 3, so a little bit below that. Okay, when we were doing the last screen here, when we did 15 milliliters, that was 12.76. So 12.76, here's 12, 13, almost 13. So we have that value. Okay, at 10, which we decided that was our equivalence point, then we found out that that pH was 9.5. So at 10 milliliters is 9.5, almost 10, halfway, here's 9. 9.5 will be up there somewhere. Okay, and when we had put 5 milliliters in, then we found out 3.59, which was the halfway point, 3.59, and that was the halfway to the equivalence point, so that was the half titration. So what do we know? We know that this part here, this is our equivalence point, that is going to be pretty much vertical, okay, and then it's going to level out, and it starts off this way, and it's kind of doesn't change too much here in the beginning because that is our buffer region. Okay, so here's our curve. Whoops, sort of missed. Okay, but that's the right idea. And that is the quick check.